Today, we want to talk about trigonometric identities. This is still intro to trigonometric identities. So it's where the teacher just like, oh, here's some trig identities. And students like, oh, great, let's see what these are. Moving on. Trig identities is where we start seeing how all the trig functions are connected. All the trig functions are related. We could see it, some of those relationships in the unit circle, but it goes beyond that. So what we're looking at when we start studying trigonometric identities is we're studying the relationships between all the trigonometric functions. We're studying the relationships among trigonometric functions. We're studying the relationships among all of our trig functions. So we want to integrate this information into our thinking. This is not just something that we want to sitting on the sidelines that we know. It's things that we want to pull together. Just like when I asked you to multiply 7 times 8, I don't want you to think about it. I just want you to know that it's 56. So when you're a kid, you get to think about what 7 times 8 means before you come up with 56. But after you move on from learning your arithmetic, you start learning other things where you are applying what you learned about arithmetic. So you don't want to spend time thinking about that stuff anymore because you've got bigger fish to fry, algebra fish. And it's going to hold you back if you're like, oh, wait a second, 7 times 8, I have to think about this for a minute. So you don't want to do that. So the same thing happens with trigonometric identities. We want to start learning the relationships among the trig functions, not so that we know them, so that we can use them. The first phase is to just start with the 3 groups that we talked about on Wednesday. Just learn them. For now, just learn them. If that means that you have to sit down and memorize them, then so be it. Better to just remember them by doing things with them. That's what the practice problems are about when you're doing trigonometric identities. Then the next phase is to start connecting them all together, and then that will reinforce your memory of the trig functions. It's similar to learning music theory. In the beginning, you start by learning music theory, and you write out your circle of fifths, and you write out what the sharps are, and you write your C major scale, and then you start learning the modes that way. You just start learning them. Then once you've started on the path to learning them and you're starting to remember what they are, you can start making connections, and that will reinforce your memory of things like the circle of fifths and all the different modes. All right, so let's review the trigonometric identities that we want to learn. And we started with the reciprocal identities. Actually, I think I started with the other ones. But let's start with the reciprocal identities. So one thing that might help us remember, I don't know how your mind remembers things or how your mind works. It's not possible for me to know that. It's probably not even possible for you to know that. I'm not even sure how my mind works. Great big mystery. But here's how we can think about the reciprocal identities. I want you to think of the reciprocal identities as defining secant, cosecant, and cotangent. I want your idea about the reciprocal identities to be that we are defining secant, cosecant, and cotangent. The reciprocal trig functions. So secant, abbreviated secant of theta, is the reciprocal of cosine. This is why we call them reciprocal identities. That's going to help us remember the category. What they're for is going to help us remember what they are. Secant of theta is 1 over cosine of theta. Cosecant theta is 1 over sine of theta. And cotangent of theta is 1 over tangent of theta. Dude, phone, if you think it's spam, just don't answer it. Don't let them call. Anyway, so reciprocal identities. Here's what they are, and it could we don't want to just separate this into some separate corner of our mind. We're establishing a relationship among some trig functions, and the reciprocal identities define the secant, cosecant, and cotangent. We had a few problems where we talked about secant as hypotenuse over adjacent. Because cosine is adjacent over hypotenuse, secant is the reciprocal of cosine. So a connection we can make is that secant was hypotenuse over adjacent, and now these things are connected. So secant, maybe in our minds we're thinking secant. I remember secant theta being defined as hypotenuse over adjacent. And this is the reciprocal of cosine. So secant is the reciprocal of cosine. The more connections we can make between things, the easier it will be for us to remember the things when we need them. So, part 1, reciprocal identities. Defining secant, cosecant, and cotangent. Next, I think the next category is called quotient identities. The quotient identities say that tangent of theta is sine theta over cosine theta. This is important because we are relating the tangent function to the sine and cosine functions. When we have our third category, the Pythagorean identities, we're going to see that sine and cosine are related. This is going to give us a relationship from sines and cosines to get us into tangents. And then by extending the other quotient identity, there's only 2, is the cotangent of theta being the reciprocal of tangent is cosine theta over sine theta. A first level, like a 0 level way to remember this is that the cotangent has the cosine on top. That's looking at this and kind of memorizing it by form, which is not always good, but it's a start. As long as we move beyond that, then that'll do for now. So the quotient identities is the primary function, let's say, is to connect the tangent to the sines and cosines. Because if we look at consider the unit circle, the x coordinate is the cosine and the y coordinate is the sine. The quotient identities bring tangent into the unit circle. So this brings tangent into the unit circle. If we think about the unit circle, and we have an angle theta, the coordinates of the points on the unit circle are cosine theta and sine theta. So if we combine the cosine theta and the sine theta, we can get the tangent theta, and that invites tangents to the unit circle. The reciprocal identities are also invited to the unit circle with the because they're writing secants and cosecants in terms of sines and cosines. We can also connect this to our right triangle trigonometry that we had before. Tangent of theta is opposite over adjacent. If I divide the opposite and adjacent by hypotenuse, divide the top and bottom by by hypotenuse, I get opposite over hypotenuse, which is sine of theta, and adjacent over hypotenuse, which is over hypotenuse, which is cosine of theta. Here, we're doing one of our the great tricks of math, multiply by 1. But in a special form. There are the three great tricks of mathematics are add 0, multiply by 1, and change your variables. Sometimes known as pulling a Kirk, change the conditions of the test. I don't like these variables, I'll trade them for new variables. Any questions? All right. Then the other trigonometric identity that we should have moving forward are the Pythagorean identities. This is also strongly connected to the unit circle. This connects the trig functions to an algebraic description of the unit circle. So here we are connecting trig functions to the algebraic description of the unit circle. The equation for the unit circle is x squared plus y squared equals 1. Circle centered at the origin with a radius of 1. So the Pythagorean identities is just taking the x equals cosine theta and y equals sine theta and putting them into the prime Pythagorean identity, which is cosine squared theta plus sine squared theta is equal to 1. This comes directly from that unit circle where x squared plus y squared equals 1. X is cosine theta, y is sine of theta. And that gives us our primary Pythagorean identity. This is the big one. There are 9 variations. This is the important one to remember. We're looking for connections. This is connecting trig functions, sine and cosine, to the algebraic description of the unit circle. X squared plus y squared is equal to 1. X is equal to the cosine of theta. Y is equal to the sine theta. So cosine squared plus sine squared is equal to 1. We have established a new relationship between cosine and sine. Then we have 8 more variations of this one, but this is the big one. In the transformers of trig identities, this is identity prime. Everything else we can get from this one. Cosine squared plus sine squared is equal to 1. Other variations of this is that cosine squared is 1 minus sine squared. Cosine squared theta is 1 minus sine squared theta. This is just taking what we know about addition and subtraction and moving things around. Maybe it's more convenient to solve it for sine, so sine squared theta is 1 minus cosine squared theta. If we include our quotient identities, we can turn our cosines and sines. Cosine squared plus sine squared is equal to 1. If we divide everything by cosine squared, we can get another variation. If we divide by cosine squared theta, we'll have cosine squared divided by cosine squared is equal to 1. Sine squared divided by cosine squared is tangent squared. 1 divided by cosine squared is secant squared. There it is. So now we have a connection between tangent squared and secant squared. This is one that came in useful to me not more than an hour ago, because I have a trig class right before, or sorry, a calculus class right before this. So we get another Pythagorean identity relating tangent squared and secant squared. Right now, I'm just asking you to remember these. And the natural question is like, well, why do I have to remember this stuff? It's because we're trying to learn our times tables for trigonometry. We're trying to learn how all these trig functions are connected. When we understand how well connected these trig functions are, we understand trigonometry better. That's the overall point. It's not like later on at your job as an engineer for SpaceX, working on the mission to Mars, and I go, oh, good thing Leach taught me my Pythagorean identities because I can replace this 1 plus tangent squared with secant squared. If you're about to do trigonometric identities by hand and stuff like that, then Elon Musk is about to walk into your cubicle and fire you, because that's crazy. But you can't get to that desk at SpaceX without a basis in trigonometry. And it's not because there's going to be some test on solving trigonometric, simplifying trigonometric expressions. I don't know, maybe there is. I haven't applied to SpaceX. I don't know, maybe they have some kind of crazy interview questions. Who knows? Someone from SpaceX. Type your experience in the comment below. Don't do that. Nate, you can do that if you want. I'm going to have this open for comments. Then we have two variations of this. I could say this is 1 plus tangent squared is secant squared. I can solve this for, this is solved for secant squared. I can solve it for tangent squared. So I could write it as tangent squared theta. And then I can put the 1 on the other side. Once again, we're just exploiting what we know already about addition and subtraction and how they're related. If A plus B is equal to C, then B is equal to C minus A. Same thing, if A plus B is equal to C, then A is equal to C minus B. So I could say that 1 is secant squared theta minus tangent squared theta. An important thing for me to admit right now is that of these three the first two I really need to know, since I do a lot of work in calculus. specifically teaching calculus, so I have to remember these kinds of things. I always forget how this one goes. I always forget the relationship between tangent squared and secant squared. I don't know why. I've been doing this for the better part of 20 years. And yet every time I have to come up with how these two are related, it's just not there. But I know I can go back to cosine squared plus sine squared is equal to 1. I know I can divide by cosine squared because I have my quotient identities. I'm learning how these things are related. So I think in part, I allow myself to forget these two pieces of information because I know that I could put it together with this one. I know I've got this one. I know I've got this one. I know I've got cosines. That's terrible for the closed captioning. I know I've got cosine squared plus sine squared equals 1. I know I've got tangent is sine over cosine. So I allow myself to forget 1 plus tangent squared is secant squared because I know I can get there by other means. Also, in the particular problem that I was doing in calculus, I know what's supposed to happen in the problem. And so I can look at what's going on. It's like, oh yeah, this is supposed to happen, so this must be the identity. More connections help us remember things, or at least look like we remember those things. There's another variation on this, because I just divided through by cosine squared. So we can also divide by sine squared theta. And so I'd have cosine squared divided by sine squared is going to be cotangent squared. Sine squared divided by sine squared is 1. And 1 divided by sine squared is cosecant. And then we'll have 2 variations on this one. I include this one for completeness. The only time I ever talk about cotangent squared plus 1 equals cosecant squared is when I'm in a trig class like I am right now. Plus 2 more. I should write it out. Plus 2 more. Just like AM gold. Any questions? I am asking you to remember a lot of things, but all these things are connected. We're trying to understand all the relationships in these trig functions. And a lot of times we could say it all comes back to the unit circle, or it all comes back to the right triangle trigonometry. It all comes back to fill in the blank. And the truth is, it doesn't all come back to one thing. It's all there all the time. We just have to pick a place to start and then just start looking around. That's all we're really doing. Picking a place to start. I picked right triangle trigonometry because it's kind of cool and we can solve some problems. And then we use that as a basis for learning the rest of the connections. Any questions? Comments? Snide remarks? How's everybody okay? All right. Moving forward, these are the trig identities. There's 1, 2, 3, 4, 5, 6, 7, 6, really 6 that you have to know. Because like I said, if you've got your cosine squared plus sine squared, make sure that that one's in place. You can get the rest. How they're connected, combining these two is how you get the other ones. Combining tangent is sine over cosine, and cosine squared plus sine squared equals 1. That's how you can get to 1 plus tangent squared equals secant squared. Spend enough time doing that, and you'll just start remembering that 1 plus tangent squared is secant squared. Don't spend enough time doing that, and you're going to have to go back and get 1 plus tangent squared is equal to secant squared. Ask me how I know. So you got your reciprocal identities, your quotient identities, and your Pythagorean identities. Remember what they are. To give you something else to connect, another way to remember these identities. It might also help you to be like, oh, okay, this is category 1, and this is category 2, and this is number 3. Some of you are going to be better off if you're like, I need to outline this, and then you can be like, oh, A, B, and C, and then A and B, and so on. If you're into outlining, this would be like A, and this would be like 1 and 2. And this could be like B, and then B1 and B2, and then C, and then C1 and C2. I'm not sure how you like to remember things. So I'm just trying to give you a bunch of options for how you can remember these things. Any questions? All right. I want to make sure everybody's okay because I'm about to turn the page literally and metaphorically because we're going on to a new big thing and it might be a little bit shocking. So, literal turning of the page. And then we're just going to go right into the next big thing. And you're like, oh, but I want to spend more time on trig identities. Well, that's, you will. The next big thing. The next big thing is the other way we measure angles. The next big thing is radians. This is the other way we measure angles. Everything on this page, I'm shouting at you. Sorry. I don't know if that's a more coffee problem or a less coffee problem, but I do know what solution I'm going to apply. Radian measure is the other way we measure angles. So let's talk about that. We know that if we go around a whole circle, then that is 360 degrees. So an angle that goes all the way around that's going to be at 360 degrees. The other way we can measure 360 degrees is say that that is 2 pi radians. 360 degrees is 2 pi radians. (360 degrees is 2 pi radians. And now I'm like, oh, I should have put this in the middle because I got to put stuff over here. This isn't paper. Don't worry that I just burned an entire piece of paper. It's reusable. I didn't write measure before, did I? It's not like I'm going to edit the video. People will see these mistakes. I leave all the other stuff in. This is the other way we measure angles. Put it in the middle this time. Ooh, side benefit, I drew a little bit better of a circle, but I put the axes kind of terrible. So 360 degrees An angle that measures 360 degrees is an angle that measures 2 pi radians. If I cut this in half, we'll be at 180 degrees. And 180 degrees is going to be pi radians. This is going to bring us up another interesting point about radians. We don't have a symbol or an abbreviation for radians. We just write pi. We understand that to mean pi radians, but we just write pi. 180 degrees is pi radians. Also, I'm doing a very bad thing here. I keep using a capital pi because I just go straight across the top, and it should be a lowercase pi. So go ahead and downvote and write negative comments in the comment section. Up here is 90 degrees, and we've cut the 180 degrees in half, so we're going to refer to 90 degrees as pi over 2. So there's no difference in meaning, at least in the way that I write them. I should be writing my pi as, I should be writing pi with a little more, it should be look a little more serious, right? Capital pi is kind of a straight across thing. That's kind of stern. But lowercase pi should have a little more style to it. But mathematicians be lazy, so I'm like, oh, pi, and it just starts becoming a mess. Down here at 0, -1, we know that this is a 270 degree angle. And so that's, if we start counting by fractions, this is one of the ways that we want to really work on this. If we start counting by fractions, this is 1 pi over 2. Pi itself is 2 pi over 2, and this is going to be down here 3 pi over 2. The end game is that you remember that 90 degrees is pi over 2 radians, 180 degrees is pi radians, 270 degrees is 3 pi over 2 radians, 360 degrees is 2 pi radians. I don't have access to how your mind works, so I don't have access to the best way for you to remember those relationships. That's the end game. Some of you are going to get there just by remembering that pi is 180. This is going to be your prime thing to remember. So 2 pi is 360, half a pi is 90, and 3/2 of a pi is 270. Some of you are going to get there by remembering that 90 degrees is pi over 2. And you're just going to count 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. So some of you are going to be reading this pi as 2 pi over 2, so that you can get to 3 pi over 2, so that you can get to 4 pi over 2. And you're reading this as 1 pi over 2. So you're counting 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. That's, I spelled 2 wrong. That's going to be your way in. Others will be like, oh, that's crazy. Pi is 180. So 90 is half of that, pi over 2. 270 is half again, 3 pi over 2. That's the way. So you're going to be dividing yourself into little different groups of Mandalorians. Some of you be like, oh, this is the way. And then the other ones will be like, oh, no, this is the way. You can take your helmet off. And then these people will be like, oh, are you crazy? You know what I mean? What we need to do, you're like, oh, dude, this seems like a big deal. And there's only like 2 minutes left. What you need to do is go all the way around the unit circle and learn your common angles in radians.
So the common angles have a 30, are at the quadrants or have a 30, 45, or 60 degree reference angle. So you need to go around the circle with a 0, 30, 45, 60, 90, 120, 135, 150, 180, that's 180, 210, and so on. You got this in degrees. Now you need to go through and get it in radians. 0, oops, I wrote theta. 0, 30, 45, 60, 90 is pi over 2, 120, 135, 150, 180 is pi, 210. You got to go all the way around your unit circle and learn to count in fractions of pi. Got to learn to count in fractions of pi. And I don't want you just to know the numbers. I want you to think about how you are going to remember these numbers. It's learn the angles. Yikes. In radians. And think about how you are going to remember these values. So you need to learn the angles in radians. I've given you 4 already. 0 you get for free. So I've given you 5. That's cheating. You got your multiples of 90 or multiples of pi over 2. 1 pi over 2, 2 pi over 3, 3 pi over 2, 4 pi over 2. Or you're going to say, whenever I see pi, that's 180. So I'm going to figure out what fractions these angles are of 180. And that's my way in. Those are the 2 most common that you'll see. Any questions? The starting assignment for this in radian measure is going to be a graded discussion where you list some of these values and then explain to everybody else how you're going to remember these values. I want you to try to put into words your strategy for remembering all the angles around the unit circle in radians, so that you know the unit circle in degrees and you know the unit circle in radians. Any questions? Comments? Snide remarks? All right, that's going to do it for today. I will see y'all on Wednesday. Thanks for playing.